Welcome to the Explainer. Today, we're going to bridge the gap between that gut feeling you get when you design something and the cold, hard math that proves it'll work. We're going to unlock the secrets behind some seriously complex mechanisms and see how these two big ideas team up to build the ultra-precise machines of tomorrow. So, let's start with this little marvel of engineering. It's called a flexure. Now, what's so cool about it is that it's monolithic. That means it's carved from one single solid piece. There are no moving parts to wear out. Its motion comes from the material itself, bending just a tiny bit, which means you get movement with zero friction. You can see why these are absolutely essential for things like super delicate scientific instruments. But here's where we hit a wall. When we start combining these simple flexures into really complex systems, our intuition, well, it starts to break down. You can't just eyeball it anymore and hope for the best. Guesswork just won't cut it. Which brings us to the big question, right? How do we move from just guessing to actually guaranteeing how these intricate designs will move? How can we be absolutely certain? Well, the solution is pretty elegant. It turns out we need to look at the problem through two different lenses. One is all about our intuition, and the other is about pure mathematical rigor. Okay, so let's check out the first lens. This is the geometric lens of constraint-based design. This is our home turf. It's the intuitive approach. We're thinking visually, sketching out ideas about all the ways a part can move, its degrees of freedom, and then thinking about the physical things that stop it from moving, the constraints. And then we have the second lens, the algebraic lens of screw theory. Now, this is where things get really powerful. It gives us a universal language, in math, to describe any motion or force in 3D space. It boils down any combination of pushing, pulling, and twisting into a single, precise, six-dimensional vector. This isn't about feel, this is all about rigor. But here's the really cool part, where it all comes together. What if these two lenses aren't actually different worlds? What if they're just two different languages describing the exact same thing? And this is basically our Rosetta Stone. It shows us how to translate directly from one language to the other. Our intuitive idea of a degree of freedom, like something spinning, becomes a mathematical object called a twist. And a physical constraint, like a stiff rod holding something in place, becomes a wrench. It's a perfect one-to-one translation. So the fundamental rule that connects them is something called reciprocity. It sounds complicated, but the idea is simple. It's a quick math check. If the wrench does no work against the twist, meaning it doesn't fight the motion at all, their special product is zero. And if it's zero, the motion is allowed. It's the ultimate go-no-go chess. Okay, so with this new shared language, we can start building an incredibly practical toolkit. It's like we're creating a catalog of our fundamental building blocks. Now, every common flexure element, a blade, a wire, you name it, gets its own unique mathematical signature. We can define the exact motions it allows, its twists, and the exact constraints it applies, its wrenches. So now we have this amazing library of parts, and each one comes with its math built right in. And when we want to combine these parts from our library, it turns out it follows two really simple rules. It all just depends on how you arrange them, either end-to-end, what we call in series, or side-by-side, which is in parallel. So, for serial chains, think of it like stacking Legos. When you connect them end-to-end, their freedoms just add up. The total range of motion for the whole system is simply the sum of all the individual motions. Simple as that. But when you connect them in parallel, the exact opposite happens. Their constraints add up. Every element you add side by side takes away some freedom, further restricting the overall motion of the entire system. All right, enough theory. Let's put this powerful combo of intuition and algebra to the test. We're going to walk through a classic example to see how this actually works out in the real world. So take a look at this, the trapezoidal flexure pivot. It's just two simple blade flexures arranged in parallel. Now, using our geometric lens, our gut feeling tells us that this setup should create a really clean pivot, a single, pure rotation around some invisible point out in space. But is our intuition right? Let's find out for sure. We can now follow a clear 5-step process using the algebra. We describe the mouth for a single blade from our library, use our parallel chain rule to combine the two of them, and then run the numbers to see what motion is left. And what do you know? The result is a perfect confirmation. The screw algebra spits out one single vector that describes that exact pure rotation we predicted. The math proves our intuition was totally spot on. And really, this is the whole point. We have a tool that doesn't just confirm our intuition, it makes it precise, it makes it predictable. That right there is the power of this synergy. So, what does all this really mean for the future of precision engineering? Well, it's a huge deal. It's a fundamental shift in how we even approach the design process. It creates this incredible feedback loop. We use our geometric intuition to dream up a concept, then we use the algebraic formulation to rigorously analyze it. And the results of that analysis, they feed right back and make our intuition even sharper for the next design. It's a cycle of constant improvement. When you get right down to it, by combining these two lenses, we are transforming Flexure design. We're moving it away from being this kind of ad hoc art form based on experience and guesswork and turning it into a truly predictable and powerful engineering science. And that leaves us with one final, really exciting question to think about. Now that we have a systematic way to translate our wildest design ideas into precise mathematics, what kind of incredible, seemingly impossible machines are we finally going to build?